P-type semiconductors. Doping. P-type semiconductors are created by adding a small amount of trivalent impurity atoms, atoms with 3 valence electrons, to a pure semiconductor material, typically silicon or germanium. Common trivalent impurities include boron, aluminum, gallium, and indium. Holes. When a trivalent impurity atom enters the semiconductor crystal lattice, it forms a hole or a vacant electron position. This hole can accept an electron from a neighboring atom, effectively moving the hole through the crystal. Majority charge carriers. In a p-type semiconductor, the majority charge carriers are holes, while electrons are the minority carriers. Conductivity. The conductivity of a p-type semiconductor is due to the movement of these holes. N-type semiconductors. Doping. N-type semiconductors are created by adding a small amount of pentavalent impurity atoms, atoms with 5 valence electrons, to a pure semiconductor material. Common pentavalent impurities include phosphorus, arsenic, antimony, and bismuth. Extra electrons. When a pentavalent impurity atom enters the semiconductor crystal lattice, it contributes an extra electron to the crystal. These extra electrons are free to move within the crystal, contributing to electrical conductivity. Majority charge carriers. In an N-type semiconductor, the majority charge carriers are electrons, while holes are the minority carriers. Conductivity. The conductivity of an N-type semiconductor is due to the movement of these extra electrons. The p-in junction. Where magic happens. When a p-type and an N-type semiconductor are brought into contact, they form a p-n junction. At this junction, a fascinating phenomenon occurs. Diffusion. Electrons from the N-type region diffuse into the p-type region to fill the holes. Similarly, holes from the p-type region diffuse into the N-type region, depletion region. This diffusion of charge carriers creates a region near the junction, known as the depletion region, where there are no mobile charge carriers. Electric field. The depletion region develops an electric field that opposes further diffusion of charge carriers, creating a barrier potential. Applications of p-type and n-type semiconductors. The combination of p-type and n-type semiconductors is the foundation for many electronic devices, including diodes, used to allow current flow in only one direction. Transistors. The building blocks of modern electronics, used for amplification and switching. Integrated circuits, ICs. Complex circuits containing millions of transistors on a single chip. Solar cells. Convert sunlight into electricity. By understanding the properties of p-type and n-type semiconductors and their behavior at the p-n junction, scientists and engineers have been able to create a vast array of electronic devices that have revolutionized our world.